Okay, this is the first of three videos that will walk you through the problems that were assigned for this particular section. The first problem that we're going to look at is problem 7510 OGG. And in this particular problem, we have an air standard cycle executing in a closed system composed of the following four processes, and they're shown over here on the right. First of all, from 1 to 2 is an isentropic compression from 1 pressure and 30 degrees Celsius to 900 kPa. And so in this particular case, even though it is a closed system, we are going to identify the compression process or the movement from one volume to another volume in terms of the pressure rise. Process 2, going from state 2 to 3, is a constant pressure during heat addition, and the heat addition amount is given as 3,000 kilograms per kilojoules per kilogram. So this is similar to what we see in the diesel cycle, where the cylinder starts to move out under constant pressure as the heat addition occurs. And so there's not only heat, but also work that's being generated. That's then followed by a third process that is from 3 to 4, which is a constant volume during some heat rejection, and the pressure goes back down to the original incoming pressure. Because it's constant volume, we know that there's no work being done. In fact, the cylinder has changed, is not moving during that particular process. And then we have a final process, and that final process is again a constant pressure at the given initial pressure where additional heat rejection occurs. And so there's heat rejection in both the third and the fourth process. And so what we're asked to determine is the maximum temperature in the cycle and to calculate the first law of thermal efficiency utilizing the PG model. Okay, so with that in mind, I'm going to bring up the test software, go into the test apps, and again, this is a closed system, internal combustion engine reciprocating cycle, and we're going to select the PG model. And so we will then begin by identifying the four states and connecting the four states together with the various processes to determine heat transfers and works. And so our first state was designated as 110 kPa with a temperature of 30 Celsius. Now, in this particular problem, as I indicated in class, since we are asked to put in a certain amount of heat in a kilojoules per kilogram, what I'm going to do is I'm going to assign the amount of mass in a single in the cylinder at this initial condition as being 1 kilogram. And so by doing this, all of the works and all of the heat transfers are going to come out in terms of kilojoules. And so when we get to the process panel where we're adding the heat, we'll be able to just put in a 3,000 kilojoule value since we have 1 kilogram of mass. And so here's our initial state. Our second state was going in an isentropic compression. I'm going to set that the mass is the same as mass 1. We have an isentropic compression, similar that we had in our auto and diesel cycles. And in this particular case, we do know the final pressure. And so under that particular scenario, we see that the volume has gone, to, let's put it in liters. The volume has gone up, down to 176 liters. Again, it's very large because we have 1 kilogram of working fluid. But if we went back to state 1, we would see that the volume is 790. So the compression actually goes from 790 to about 176. And so it's about a 5-to-1 compression ratio. Okay, so now we're ready. We've identified state 2. We're now ready to go to state 3. And again, state 3 was the case where we had the heat addition at constant pressure. So between 2 and 3, we know the pressure stays the same. And it's equal to P2. And again, the mass is equal to the mass at 1. Okay, so and now in this particular case, it's the process panel that's going to give us enough information to determine the final thermodynamic property. And so we'll wait for that to happen. We'll then go to state 4. And what we know about state 4 is state 4 is, state 4, between 3 and 4, we have a constant volume heat rejection. And so down to 110 kPa. So state 4 is a constant volume process, and so the volume is the same as volume 3. The mass is equal to M1, and the pressure went down to P1. And so we have, again, one thermodynamic state. We know what the second thermodynamic state is as soon as we calculate state 3. And so we have the 4 states. As it goes from 4 to 1, that's going to be a constant pressure process. And so we're now ready to go to the process panel. And we want to, first of all, put in the compression, the isentropic compression. No heat transfer for an isentropic compression. And we see that for that 1 kilogram of mass, there's a certain amount of kilojoules required of work in order to compress it. We then go to process 2. Now process 2 was from 2 to 3, and this was that constant pressure heat addition, and the amount of heat that was added was 3,000 kilojoules per kilogram. And so in this particular process panel, we just put in 3,000 kilojoules because we have a system that is 1 kilogram in size. Now, in this particular case, there's no shaft and there's no electrical work, and so we're going to say that WB in this, because it is a, on this particular case, we know that there's heat transfer, there is work. It's going to calculate the work for us. We're then going to go to process 3. And process 3 is the constant volume due to a heat rejection. And so process 3 goes from 3 to 4. And again, there's heat rejection, and it's a constant volume process. And so the one thing we know about a constant volume process is that there's no boundary work. Okay, and so it's going to then, it will also calculate the heat transfer, the heat rejection. And then finally, our final process is from 4 back to 1. And that was a constant pressure process. And so in that particular case, we do have some work and we have some heat transfer. So what we're going to do then is we're going to go back and we're going to do a super calculate. And we're going to go and take a look at our state panels now. And we see if everything has been calculated. So in state 1, we started with a temperature and pressure and a mass. State 2 went up 900. It was isentropic, and we see that it went up to this temperature. Again, constant mass. State 3 then was that constant pressure process where it went up to an elevated temperature of 3,542 Kelvin. Again, constant mass. And then finally, state 4, which was a constant, is at the same pressure as the final pressure. We see because it's constant volume, we see that the temperature has dropped to 430 432. And so as you can see here, the volume at state 4 is one, put it in liters, is 1128 in liters. If we went back, we see that 1128.29, this was the same volume between 3 and 4. Back in volume 2, we saw that was 176. And so as the heat went in between 2 and 3, we see that the volume changed by a considerable amount during that during that heat addition work process. And so now, since we have all of the various states identified, we can now go back to the process, and we see that the work of the compression is now determined. During that heat addition, we had some power being generated, some work being generated. We then had some rejection of heat with no work because it was there was no boundary work because of the constant volume. And then finally, in our last rejection, we had a little bit of negative work being done. It is compressing, and we had some rejection of heat. And so we have all of our state points. We have our 4 processes tying everything together. We can look then at the cycle panel to answer the questions. The question was, what's the maximum temperature in the cycle? And that maximum temperature that we saw was 3,542. It then asks us also for the thermal efficiency. And the thermal efficiency determines, again, for that 1 unit of mass, it figured out how much work was generated and how much compressive work was required. And so it took the difference in these two, which was the net work, and then it divided it by the heat transfer that we had to supply. Again, the amount of heat transfer for 1 kilogram. And so our thermal efficiency is 641 over 3,000, and that calculates to 2138. 21.4% is our thermal efficiency, and our maximum temperature is 3542. Now, if we wanted to, we could go to our graphics panel, and we could take a look at what this looks like on the TS diagram. And we can compare that to what we saw before, and what we saw before, what was given in the problem, maybe looks a little bit different. And again, it's just because of the scale. So here was our 1 to 2, that was our first compression. We then had that constant pressure process up to 3. Now, if I were to say, let us put through state 2 a constant pressure line, we see that that's the constant pressure line. And then from 3 to 4, we actually had a constant volume line. And so through 3, I can then draw the constant volume line. And then finally through 4, I can finish it up by looking at a constant pressure line. And so there's the constant pressure line. To be complete, I can say through 1, let's go ahead and put in a constant entropy line. And then we have the full diagram. Here's our 1, 2, our 1 to 3, our 3 to 4, and finally our 4 back to 1. And again, we can go to the I/O panel, do a super calculate, and have all of the information that we would need in order to copy and paste and store for a future. Okay, with that, I'm going to close off this video.